Good morning, students. It is May 18th. It's about 8:45 at my house, and I'm going to post this for you by 9:30. I wanted to give you a little bit of practice with Ohm's law, having to do with electric current and voltage and resistance. And then I wanted to show you some schematic symbols, the symbolism that is used in creating schematic diagrams for electronic systems. All right, you're going to see that in some of your homework this week. And so here we go. So just a little review of Ohm's law. Let's see, I'll pick purple. So Ohm's law says what? That current is directly proportional to voltage and it is indirectly proportional to resistance. So that means when there's a lot of voltage, the current tends to be high. And if there's a lot of resistance, the current tends to be low. All other things being equal. And again, what do we know about current? Current measures in amps. And an amp is a volt per ohm. We have voltage that gives us some potential energy. It's actually potential energy per charge. Potential energy is a joule per charge. Charge measures in coulombs. Okay, so a volt is a joule per coulomb. And then we have resistance. Resistance measures in ohms. And an ohm is the same thing as what? A volt per amp. All right. We also know that an amp is a really large amount of current. So 1 amp is huge. So current tends to be much lesser in quantity. So on the order of milliamps, 1/1000th of an amp is usually what we see. Although household circuits are rated for 10 to 15, sometimes even 20 amps in an entire circuit in one of your rooms in your house. And so your house does draw a lot of current because you probably run a lot of appliances. All right, and so we're going to be practicing with this formula today, and just keep in mind that you can write this a few different ways. You can write it as I is equal to V over R, or you can write it as V is equal to I times R, or you can even solve it for resistance if you want to. And what would that look like? Resistance is equal to voltage divided by current. All right. And so a few different ways to write that formula. We also have another formula that's going to be important. It's the power formula. So power, what is power measured in watts? Power is voltage times current. And how do we get a watt from that? Well, voltage is a joule per coulomb, and current amps is really a coulomb per second. And so we see here that coulombs cancel, and you end up with a joule per coulomb, a joule per second, which is the same thing as a watt. And so we can figure out how much power a circuit draws by using the power formula, keeping in mind that I could write voltage here. I could write voltage as I times R, right? Or I could write current as V divided by R if I wanted to. So there's a few different ways to write that power equation as well, and we'll see that in our examples. Okay, so that's what we're going to be working with. What about schematic symbols? And so when we put together a circuit, remember a circuit is a complete loop. Circuit has to be a complete loop for current to flow. If there's any gap in a circuit, then current is not going to flow. And so last week, I should say, not yesterday, we drew this little, battery. And then in place of a resistor, I put a little light bulb, and back to the battery again. That's my complete loop, and current is flowing from the positive and into the negative and right through the battery that way. All right. Well, that's not really a schematic drawing. It is not a schematic. So what is the symbol for a battery? A battery has a long side and a short side connected with some wires. All right. The long side is the positive side. So that is the symbol for a battery. A light bulb looks like a circle with a little loop-de-loop in it. There's a light bulb. And sometimes a light bulb is just shown as a resistor. And in general, a resistor is something that looks like this, so sort of a sawtooth pattern. That is a resistor. Okay, so light bulbs and resistors are interchangeable because a light bulb is a type of resistor. All right, what else might you put in a circuit? Light bulbs, batteries, resistors. You might have something that looks like this in a circuit, and that's known as a switch. Okay, you could also have something that looks like, it almost looks like a switch with a little squiggly in it. That's known as a circuit breaker or a fuse. In old houses, they had fuses. This little squiggly line in here indicates a little filament that melts if the current gets too high. So if the current gets high, that little filament melts, it breaks the circuit, and current stops flowing. So that's another type of circuit element that you could see. All right, and there are a bunch more. Trying to think of other ones that we might be using, and I don't think there are any more that we're actually going to use for the remainder of the year. So I think that's a pretty good list. So regardless of that, if any other circuit elements pop up, I'll talk to you about them. But let's redraw this in schematic format. And so in place of the battery, I'm going to put, oops, I want to be using purple. I'm going to put long side and short side. Here's my wire. And I'm going to draw the bulb to look like this. Okay, so there is my schematic. This means the same thing. You're going to see this kind of circuit drawing in your homework. So out of the positive side and into the negative side, that's the way current flows. We're going to be measuring voltage across different elements. Next week, we're going to be getting some practice with that using different types of meters. But this week, we're just going to be practicing using Ohm's law and drawing these little circuit diagrams. Okay, it would also be perfectly correct to draw this using a resistor. All right, so the bulb is also a resistor, and again, the long side is the positive side of the battery, and I'm going to show my direction of current flowing around that loop like that. Okay, so those are some circuit drawings. There you go. On to a few examples. I'd like to do a couple of examples. I'm going to encourage you to always draw a picture when you're doing an Ohm's law problem. Always, always, always draw a picture. The pictures will eventually get, or the systems will eventually get more complicated. So if you develop good practice skills in drawing your pictures, you'll be ready for those. Next week, we're going to be putting bunches of resistors together and seeing if we can solve systems that have more than one resistor in the circuit, maybe 3 light bulbs or 4 light bulbs, or maybe a dishwasher and a refrigerator and an oven in our kitchen. Okay, so we'll be adding resistors together. Okay, so example 1, 12 volts of potential, that's the voltage of a car battery, pushes current through the starter solenoid, that's what starts your car, and that solenoid has a resistance of 50 ohms. How much current flows through the solenoid? Okay, so I see a battery, 12-volt battery, and I see this thing that is called a solenoid. I don't really know what that is, or you might not really know what that is, but it offers a resistance. So I can assume that that is a resistor. So 1 battery, 1 resistor. I'm going to go ahead and draw that simple circuit. There's my battery. There's my resistor. And I'm going to label it 12 volts and 50 ohms. 50 ohms. And the challenge is to find the current. All right? And so we can do that. So I have Ohm's law. I is equal to V divided by R. Now I write down Ohm's law and I just plug in what I have, 12 volts divided by 50 ohms. I get out my calculator. 12 divided by 50. And I see I have 0.24 amps, which is the same as 240 milliamps. So thinking about, how much current hurts us, that is a lot of current in milliamps. 1 milliamp of current is enough to hurt us. And so 240 milliamps is definitely a lot of current. Either way you write this, it's correct. Remember that there are 1,000 milliamps in 1 amp. Milli means 1/1000th. Okay, so 1 milliamp is 1/1000th of an amp. So keeping in mind your conversions. All right, here's another one. 110 volts of potential from a household outlet. That's what you have in your house. Powers a light bulb, which has 150 milliamps of current. How much resistance does the bulb offer? So again, I'm looking at this problem. I have a voltage, I have a current, and I'm asked for resistance. So I have Ohm's law. I'm going to rewrite that to solve for R, V divided by I. And I'm given 150 milliamps. I better write this in amps. So 150 milliamps is the same as 150 times 10 to the negative 3 amps, milli meaning 10 to the negative 3. And this is 0.150 amps. So that's how much current I have. So the resistance, 110 volts divided by 0.150 amps. Take out your calculator. And I get about 733 ohms of resistance in that light bulb. All right. One more problem. This one is a little bit different, but you will have some like this. And so let's see what we have. 110 volts of potential powers a bulb that's rated at 60 watts. Well, if you ever bought a light bulb, you know that they're rated in terms of wattage, how much power they convert from electrical energy into light and heat. And so 110 volts, 60 watts. So now I need to think about the power equation. I'm not given anything about current. I'm not given any resistance. I'm asked to find the resistance. So I'm going to have to use this power equation. Power is equal to voltage times current. Okay, how am I going to use that to find resistance? Well, think about the fact that you can write voltage as IR, but you could also write current as V divided by R. Remember, current, we defined current as voltage divided by resistance. If I plug that in here, power is equal to voltage times current, I get a new formula for power, V squared divided by R. And that's going to help me because in this case, I want the resistance and I'm given the voltage and I'm also given the power. So I don't have any information about current. So if I take this power formula, V squared divided by R, and I multiply by R, power times R is equal to V squared. And then I divide by power. So here we are doing a little bit of algebra. I get R is equal to V squared divided by the power. And that is exactly what I need to use. So now I'm going to plug in 110 volts, need to square it. I'm going to divide by the power, which is 60 watts. Okay. And that should give me the resistance. So 110, square that number, I get 12,100 volts squared divided by 60. Remember, a watt is really a volt times a current, a volt times an amp. So divide by 60. And I get about 201. Being careful with our units. One of the volts cancels. 201 volts per amp. And remember, a volt per amp is the same thing as an ohm. So the resistance is about 201. It's actually closer to 202, looking at my calculator. 202 ohms of current. There we go. So you're going to have some problems like this. They involve a little bit of algebra. Make sure you work them out. I will post the solutions next week. All right. And so you're going to have a couple of things to do. You're going to have a worksheet to do this week with practice for Ohm's law. And I'm also going to have you practice using the FET simulation, which has you putting little circuits together and measuring things. All right. So that's it for this week. Have a good week.